Okay, I'm working in a slightly older version of Autodesk Simulation. This will be version 2011, which looks considerably different from 2012, which you guys will probably be using. But what I wanted to do was show you in general how to set up a quick axisymmetric problem. Now you'll remember for a problem to be in 2D, it has to be in the YZ plane. So putting it here in the YZ plane. Okay, next thing. You have to set it up so that the axis of symmetry is in the Z direction. Okay, and remember I said if it's solid, then your cross-section will start at Z equals 0. If it's not solid, your cross-section is not going to start there. So let me just show you real quick what I mean. I'm going to go ahead and create a line. Some of this will look quite similar to what we've been using. I'm going to start out at 0, 0. Now, if you recall, the pressure vessel we looked at had an inner radius of 5 inches and an outer radius of 10 inches. So I'm going to put my next point 5 inches in the Y direction, and then I'm going to take as a slice, let's say, let's make it 5 inches high for height on it. So that would be DZ is 5 inches. Okay, now, outer radius 10 inches, inner radius 5 inches. That means the thickness is 5 inches. So I'm going to go over here another 5 inches in Y. Okay, and go down 5 inches in Z and connect back right here. Okay, now I'm going to delete this line. I need to select a construction object, and I'm going to get rid of this line. Okay, so this point, remember, represents the origin. That will be at 0, 0. Right. Now, next thing I want to do is look at the coordinate systems. I'd like to change the coordinate system. Okay, so let's see about doing that. In fact, best thing to do on that, go ahead and go to Help Files. It's been a while since I've changed up the coordinate system, but you guys should be able to pull up the same information in yours. Let's look at how to change the coordinate system. Okay, go under Search. Okay, local coordinate system. Okay, create coordinate system. So we right-click on the heading in the environment and select New. Close this out. So I right-click here on Coordinate Systems, select New. What we're going to want is a cylindrical coordinate system. Let's see. For Z, okay, let me point this out to you guys for a second. Point A will be where our origin will be. Now this will be very, very similar to what you'll see in your current version of Autodesk Simulation. A is our origin. Let's leave our origin at 0, 0, 0. Okay? So point B. Point B establishes what the Z direction will be. Well, that for us will be Z. So let's just go ahead and put point B at 5 inches in Z. Point C establishes the X direction. So let's put point C at 5x. Okay? Now that should give us a sensible coordinate system. Double check again. Our origin is at 0, 0, 0. Point B is at Z equals 5 inches. Okay, point C would be at X equals 5 inches. Okay. Alright, so now let's set up our element type. Remember, you go to 2D. It's thinking for a moment. And for element definition, the geometry type is not plane stress. Make sure you set it to axisymmetric. I'm going to leave everything else as it is. Thickness, Autodesk will automatically use a 1 radian thickness. Okay, so let's stick with this. Let's go OK. For a material, let's just use a steel. Let's see, I want I'll go with AISI 202 stainless. Use whatever material that you'd like to use. Okay, next step is to mesh our model. So I'm going to right click down here on meshes. Right click on the construction objects that make up our part and create a 2D mesh. And I'm partial to triangular elements, so I'm just going to go ahead and use triangular and leave everything as it is, and let's click apply. It's thinking. Okay, there's our mesh. Now let's apply our load. So I'm going to go select, and I'll go with surface. Select that surface, add. We're going to go with surface pressure traction. Click on that. And I believe that pressure was 100 psi. And I'm going to just put under description internal pressure load. Okay, next we need to add a boundary condition to this bottom edge. Okay. Okay, so adding our boundary condition, I've selected that surface, right click, add surface boundary condition. Alright, well, we know that it's possible for the radius, interior, exterior, anywhere in between radius, to change due to the loadings. So we can't completely constrain Y. We do need to constrain it in X. There's no theta displacement allowed. I don't believe we need to constrain it in Z, but I do say let's constrain it for no rotation. Now what I want to do is try this set of boundary conditions and see if it's enough to prevent rigid body motion. Okay, so let's go ahead and run an analysis of this. As you can see, this looks a little bit different from what you're used to in the latest version of Autodesk. They have tabs. We have buttons. It's hard to get used to the buttons and go to the tabs, but you know, hey. Let's see. It did not finish. See. Let's go details. Okay, should pop up with an explanation, hopefully, of what went wrong. It doesn't, so let's do check model. Okay, the model check came through all right. So I'm going to go, I'm not getting any errors. It's showing loads applied. I'm going to try this one more time. In the older version of Algor, sometimes it won't run. You go through check model, then run the simulation again, and it will work. And indeed now it is working. So let's change our view a little bit so we can see a bit more of our problem here. We see our pressure load. It is applied in the correct direction. Let's look at our displacement results. Let's focus on magnitude. Okay, hey, this is good. Displacement's very small, so we don't have any rigid body motion. Now, remember I went to a lot of effort to set up a cylindrical coordinate system. I want to view our results in terms of that cylindrical coordinate system. Okay, let's go to results, stress, stress tensor. Let's look at XX. So that, you'll notice it changes it up here, stress tensor RR. This is our radial stress. It's going from negative 89 psi to negative 1.7 psi, with maximum being at the interior surface. Okay, let's look at stress tensor. Let's look at YY stress. That's theta stress. Okay, so our theta stress is going from 65.5 to 173.6, maximum being at the interior surface. Okay, let's look at ZZ stress, almost negligible. Okay, We can also look at shear stress. Let's look at von Mises stress now. Maximum is at the interior surface at 227.968. Now there's two things we need to ask. Number one, is this a correct solution? Does this match kind of what theory would predict? We'll talk about that in a second. Number two, how much discretization error do we have? So for results options, let's turn off smoothing. Not too terribly smooth here as far as our stress results go. What I'm going to do is set up an Excel spreadsheet to keep track of this and see how our solution converges. And I'm just going to go ahead and kind of demonstrate for you guys how to do this. I'm opening up Excel. I'm going to call this this will be von Mises, and I'm getting a maximum of about 228. Now I need to know how many nodes, at least how many nodes or elements we have. I'm going to go to Inquire, Model Statistics, and we've got 197 nodes. So let's put that in here, 197 for nodes. Now let's look at our precision, results, stress, precision of von Mises stress. Oh, I don't even need to remesh this, guys. In fact, I'm not even going to bother setting up the spreadsheet, I don't think, because we're going from 0 is minimum, maximum is 0.03 on a scale of 0 to 0.5. That's really, really good. I really don't think we need to remesh, but we could just to see what happens. Let me enter the precision here of 0.033. Okay. And with a cylindrical problem, you'd also want to enter like the hoop stress, radial stress. But right now I just want to see if it's converging. I'm going to focus on von Mises. Okay. Now let's go back and refine the mesh. So I'm going to go back to my tab for FEA analysis. Right click on my mesh. I'll modify it. And let's double the mesh density to 800. And we'll run it again. Let's see what we get. Okay, our von Mises precision is now at 0.0236. Let's see what our von Mises stress is. 229.5. Not much of a change there. Inquire, model statistics. Got 361 nodes. Okay. So not too much of a change there. In fact, let's see what the percent change is. I'm going to take this minus this and divide it by, I guess, the original. So we're getting a percent change of 0.66%. I think this is definitely a good solution. I think we've remeshed it enough. Okay, so I feel comfortable with this solution. This shows you how to set up a cylindrical type problem, how to analyze it, and remember how easy it was to set up that cylindrical coordinate system.